Alright guys, last MO theory video. So we just introduced the oxygen molecule O2. It has every appearance of being a diamagnetic molecule, meaning it looks like all the electrons are paired up, but we know from its properties that actually it does have unpaired electrons, but we need to prove that. How can we prove that? So we're going to do the MO diagram of oxygen, and we're hoping that it's going to show us that oxygen does have unpaired electrons because its properties indicate that it does. Now, when I bring two oxygen atoms together, this one's going to be a little bit more complicated than hydrogen and helium, because instead of doing the first row where all I had was an s orbital from one and an s orbital from the other, now I'm in the second row. There are more orbitals involved. The first oxygen atom, now again, we usually are still going to just focus on the valence shell. So for oxygen, we're going to ignore the first shell, because what would happen in the first shell, if we tried to overlap, the bonding and anti-bonding would just cancel each other out. So we really just want to look at the valence shell. That's where all the action's going to happen. So oxygen has 2s and 2p orbitals, and in the valence shell, this oxygen atom is going to have 6 electrons. The other oxygen atom also has a 2s and 2p orbitals. It also has 6 electrons. So the molecule altogether has 8 orbitals and 12 electrons to deal with. All of those need to be represented in my MO diagram. So the way we do it, and typically on a test, regardless of whether we're online or in class, typically in an in-class test, I would not make you draw this diagram out. I would probably provide the diagram on the test. You have to be able to label it and fill everything in. Okay? So, what happens when we overlap the orbitals of oxygen? Well, first of all, the s orbitals are going to overlap with each other, then the p orbitals are going to overlap with each other. So first the s's, when they overlap, I get an orbital that went down, an orbital that went up, so that's my bonding and my anti-bonding. The way we usually label them, if s orbitals overlap, it has to overlap between the atoms. So s orbitals always overlap to give a sigma bond. So it's a sigma, and then the 2s is just representing it's the 2s orbital. So it's the sigma bond that would form from the overlap of 2s orbitals between the oxygens. Bonding, anti-bonding. The anti-bonding one has a star beside it. That's just how we denote the anti-bonding orbitals. Okay? Then when the p orbitals overlap, it gets a little weird, because we actually get the orbitals splitting into different levels. Okay? So there are 3 orbitals here, there are 3 orbitals here. When they overlap, that's 3 and 3, we're going to get 6 orbitals in the middle. 3 of them went down, so these 3 are bonding. 3 of them went up, so those are anti-bonding. Now, why are the 3 bondings not at the same level? Well, it's usually based on the orientation of the orbitals. Again, if we think about p orbitals, there's px, py, and pz. They're all perpendicular. Only one of those 3 orbitals can be pointed at another atom. If I point one of them, let's call it the px orbital at another atom, the py and the pz's are perpendicular to that other atom. Well, we've said previously, the one that's pointed straight at the other atom can give direct overlap between the atoms. That's going to be a sigma bond. That's a really strong interaction. So an orbital that can form a sigma bond is going to cause a more drastic drop in energy. The energy level of the sigma orbital is going to be lower than the other 2, which are perpendicular to the other atom. So pi bond can form from the vertical one reaching over the top and underneath. That's not as good. It doesn't save quite as much energy. So one of these is going to be the vertical pi bond. The other one's going to be the around the sides pi bond, or horizontal. So that's why we get the splitting here. Now you can get some variations the book will get into, but don't worry about that too much. We don't want to get too bogged down in this. But I get 3 bonding orbitals, the sigma and the 2 pi's, and then I get the 3 anti-bondings, which have to be a mirror image. If the sigma orbital is lower than the pi's, then the sigma anti-bonding has to be higher, because they always have to be opposite of each other. Now, I've got all my orbitals. If you count them up, there are 8 molecular orbitals in the middle. Now I need to put my 12 electrons in. So as I click through, the first two, there's 1, there's 2, there's 3, and 4. So the first 4 all go down here. Then I'm going to move up. Again, we're just working our way from the bottom to top. There's 5 and 6, 7, 8, 9, 10. I do go 1 in each before I pair them up. I'm up to 10 now. And then numbers 11 and 12 go up here. Now, we said in the beginning I had 12 electrons. We put our 12 electrons in. When we drew the Lewis dot structure, if you look back, the Lewis dot structure made it look like all the electrons were paired up. But now we can see, if we analyze this diagram, according to MO theory, the oxygen molecule actually has 2 electrons that are by themselves. Each of those is an orbital by itself. So that's what gives the oxygen molecule it's affected by a magnet, so that's what gives it the magnetic properties. The word we use for that is something is affected by a magnet. It has unpaired electrons. We call that a paramagnetic molecule. Okay, so we have diamagnetic molecules that have all the electrons paired up. They're unaffected by a magnet. We have paramagnetic molecules that have unpaired electrons, and if you bring a magnet up to them, they will be either attracted or repelled by the magnet. So this is one of the important things that MO theory offers us that valence bond theory doesn't. Now, what if I wanted to calculate the bond order? Can we do it? Well, so I would do 1/2, and then have parentheses. The first number I need in parentheses is the bonding electrons. Basically, any of the orbitals that went down are bonding. So I have 2 here, and then I have 6 here. So my bonding electrons, it'll be 1/2 of 8 for the bonding, minus 2 here for anti-bonding, and then 2 more up here. So it's going to be 1/2 of 8 minus 4. That would give me a bond order of 2. So even though, if I go way back, the O2 molecule, it messed up how the electrons are paired because some of the electrons should be by themselves, but it did not mess up the double bond. So the Lewis dot structure is not entirely wrong. It's just not a fully accurate description because some of the properties can't be predicted. Now, when we look at actual diagrams and how these orbitals overlap, the sigma is the 2 p orbitals that are pointed toward each other. Excuse me. The pi orbitals are the 2 p orbitals that are lined up, so overlap top and bottom. When we talked about the bonding and anti-bonding, these 2 p orbitals are in phase with each other, so they're adding constructively because they're lined up the right way. If I go to the mirror image above it, I see that they're actually turned the stripes on top versus the stripes on the bottom. That means they're out of phase with each other, so they would add destructively. That's why that would be an anti-bonding up there and a bonding here. Again, the schematics will kind of take you a little further with this. This won't come up again for you guys until you get to organic chemistry. But at that point, if you have some understanding of this stuff, it'll help you understand how some reactions occur that you guys will look at in those classes. And that shows like when we combine the orbitals, if they overlap in phase, if I go to the next slide, you actually see that they actually connect across. If they overlap out of phase, that's where I get these nodes in between that represents my anti-bonding orbitals that I see. Now, the bigger the molecule is, the more orbitals we have to deal with, the more complicated everything can get. So if we were looking at this compound, which is called 1,4-butadiene, you'd have to say, okay, every carbon atom is going to have an s orbital and 3 p orbitals. Every hydrogen atom is going to have an s orbital. So if you add them all up for that still pretty small molecule, there would be 22 orbitals that you'd have to draw in your MO diagram and decide how they're going to overlap and which ones are going to be bonding and anti-bonding, and it just gets complicated. So for us, we're going to stick with diatomic. but just realize that's one of the weaknesses of MO theory, is trying to get all that stuff set up and not make any mistakes. So, blah, blah, blah. That's pretty much it. In conclusion, if I give you a molecule, it'll be a diatomic molecule. If it's like hydrogen or helium, I might ask you to draw out the whole MO diagram yourself, where the two 1s orbitals overlap. You get a bonding orbital and anti-bonding orbital. Then you fill in your electrons, and then you calculate your bond order. Once you have your diagram filled, I might ask you, would this molecule be paramagnetic or diamagnetic? And you just look to see if all the electrons are paired up. If they are all paired up, that's diamagnetic. If they're not all paired up, it's paramagnetic. That's it. So fill in the diagram, calculate the bond order, answer whether it's paramagnetic or diamagnetic. If I gave you bigger atoms like oxygen or carbon or nitrogen, I'll typically provide the MO diagram, but you might have to label what are all the names of the orbitals, fill in the electrons, and again calculate bond order and tell me about the magnetic properties. That's it for MO theory. Next one will be chapter 10.